Okay, so this is the last section from the chapter. This is 4-6. For the daily review, you're going to solve each equation by factoring. So with number 1, you're going to factor a GCF first. And then once you take out your GCF, you should be able to factor your trinomial that you have into 2 binomials. And then set each one of those factors equal to 0. You should have 3 answers then, 3 solutions for this one. Number 2, since you have 4 terms, again, once you set this equal to 0, so bring that 9x over, make it a negative 9x, you are going to factor by grouping, which we did in 4-4. The next one, again, once you bring this over, it's going to be quadratic type. So you're going to your factors are going to be x squared minus something times x squared minus something, which you can break both of those down even further then. And then 4 is just like number 1, where you're going to factor a GCF, and then you'll have 2 binomial factors that you can set equal to 0 and solve. So this is 4-6, which is the fundamental theorem of algebra. This is basically just like a summary of everything so far in the chapter. So a real number is called a root of the polynomial, and p of x equals 0. So the polynomial with an x value of the root is going to equal 0. This is what we did really in 4-5 when we were finding all of the roots with technology, especially with Desmos. R, the root, is an x-intercept of the graph of p of x. So again, you're looking at your x-axis. So we have something that looks like this. It's just a really rough sketch of our polynomial. Let's say it looks something like this. Then x equals negative 1 is going to be a root. X equals negative 2 is going to be a root. And then x equals positive 2 is going to be a root. Roots and factors have opposite signs. So if we're using this as our roots, then our factors would be x plus 1, x plus 2, and x minus 2. Again, it's always opposite signs from the roots. This goes back to 4-4. So when you divide the polynomial by x minus r, then the remainder is 0. So that's when we say whether it's a factor or not a factor. And then r is also called a 0 of your polynomial. So you can use this information to write a polynomial function when given in zeros, which is what we're going to do in example 1. And there's really only one example of this type. So make sure that you go back and you watch it again if you need to understand and just to double check and make sure that you're doing everything right. So this goes back to 4-2, which is polynomial multiplication. So it's really not a difficult skill. You just need to know what to do with this. So our polynomial, p of x, is going to be equal to, we want the simplest polynomial with roots of negative 1, 2/3, and 4. So if our root is negative 1, that means that our factor is going to be x plus 1. If our root is 2/3, that means our factor is the opposite sign, so it's going to be x minus 2/3. And then again, same thing, so if we have a root at 4, then our factor is going to be x minus 4. So multiplication is commutative, which means it doesn't matter which order you multiply in. I'd rather deal with my fraction last. So I'm going to multiply x plus 1 and x minus 4 together first. So you can either FOIL or use a box in order to multiply. So I have x plus 1 and x minus 4, and that's going to give me x squared 1x minus 4x and minus 4. And when I combine like terms from that, then we're going to have x squared minus 3x minus 4. And then we still have one more step then with our other factor that we have to multiply by. So we have to multiply by x minus 2/3. If you did x plus 1 times x minus 2/3 first, and then multiplied by x minus 4, you'd get the same exact answer. You're just going to have fractions the whole way through your problem then. So in this case, we have 3 terms and 2 terms. So we're going to have a binomial times a trinomial. So we have x squared minus 3x minus 4, and we're multiplying that by x and minus 2/3. So x times x squared is x to the third. It's going to give us negative 3x squared. This is going to give us negative 4x. This is negative 2/3 x squared. This would be a positive 2x. And then we're going to get a positive 8/3 as our constant term. The only one that's a little bit tricky when we combine our like terms is this one, because we have to add a fraction to an integer. So we need common denominators. So negative 2/3 plus negative 3/1. Common denominator is going to be 3. So we'd have negative 2/3 plus negative 9/3, which is going to give us negative 11/3 for our x squared term. And everything else is pretty simple. So our polynomial, that's going to have roots of the simplest polynomial with roots of negative 1, 2/3, and 4, is going to be x to the third minus 11/3 x squared minus 2x plus 8/3 plus 8/3. There's your simplest polynomial with the given roots. So it is a good idea just to double check and make sure that you did it correctly. So kind of thinking the other way, if we take this and we plug it into Desmos then, and then we check, there's our polynomial, x to the third minus 11/3 x squared minus 2x plus 8/3. And if we check these roots then, where this crosses the x-axis, you can see then we have our root at negative 1, and then we have our root at 0.667, which is an approximation for 2/3. And then we also have our root at 4. So you would know then for sure that's our polynomial with the correct given roots. So here's example 1 practice. Again, remember that your roots and your factors are opposite signs. So you'll have x plus 2, x minus 2, and x minus 4 for A. And then for B, if you have a root of 0, that's just going to be x. You don't have to write x plus or minus 0. It's just going to make it a little bit more complicated, but if you want to, you can. You can multiply a binomial with a 0 if you want to, or you can just distribute it through. So make sure that you do these correctly and reach out if you have any questions. Okay, so this kind of gets us into the fundamental theorem of algebra, which we've indirectly been talking about. So the degree of the function in example 1 is the same as the number of zeros. So looking at this one, the degree of our polynomial, this is to the third power, and we have 3 zeros. So this is true for all polynomial functions. So all the zeros are not necessarily real zeros. So everything that we've looked at so far, we've had real zeros. We've had things like x equals 4, or x equals negative 2, or even when we used the quadratic formula, we got like x equals 1 plus the square root of 5, and 1 minus the square root of 5. So all of those are real. We can also get complex zeros that are not real zeros. So in this section, we're moving into like x equals 3i, and x equals negative 3i, or x equals 1 plus 3i, or x equals 1 minus 3i, or 7i, or I times the square root of 7, or whatever, but any kind of complex number then that you can think about. So every polynomial function of degree n greater than or equal to 1 has at least one 0, where a 0 may be a complex number. And then the corollary to that, every polynomial function of degree n greater than or equal to 1 has exactly n zeros, including our multiplicities. So using this theorem, you can write any polynomial function in factor form. To find all of the roots of a polynomial equation, we can use the rational root theorem, irrational root theorem, and methods for finding complex roots, such as the quadratic formula. So this is going to be where we look to the Desmos first. Again, we did this in 4.5. Now we're just doing this where you can end up with complex solutions. So you're going to go to Desmos and you're going to get your x-intercepts. And then we have to, after we do that, we have to divide each rational root out. So divide each rational root from the polynomial. And then once you've done that, you are going to solve the quadratic. That's left to find all the other, to find both the irrational or complex roots. This is one of the longer processes of Algebra 2. So again, you may need to go back and watch this video or parts of this video multiple times to understand what's going on, and you're really going to figure out when you practice it on your own. So please, please, please reach out, ask questions if you need help, especially when you're working on your assignment tomorrow. So here's example 2. We have x to the 4th minus 3x to the 3rd plus 5x squared minus 27x minus 36 by finding all roots. So it's a good idea to look to see if we can factor. There's 5 terms. We have no real strategies for factoring 5 terms when there isn't a GCF. So we're going to Desmos to find our x-intercepts. So that's x to the 4th minus 3x to the 3rd plus 5x squared minus 27x minus 36. So looking at this graph, I can see I have roots, real roots at -1 and 4. So x equals -1 is going to be one of our roots to this equation, and x equals 4 is going to be the other. But because we have an exponent of 4, we're going to need 2 more roots to completely solve this polynomial, to find all of the roots of our polynomial equation. So once we have those from Desmos, that's all we really need from there. And we can divide. It does not matter at all which order we divide in. So remember, when we're dividing by the factors, it's the opposite sign. So we're going to take this expression and we're going to divide by x plus 1, because the roots and the factors are the opposite. So when we go to use synthetic division, we actually use the same sign, the exact same number as the root that we get from our calculator, from technology. So we're using -1, and then the coefficients of our polynomial are 1, -3, 5, -27, and -36. So with synthetic division, bring down our first term, multiply, we get -1, add those, we get -4. -4 times -1 is +4. Oops, that's going to give us 9, not 4. 9 times -1 is -9. Add those, we get -36. Negative times negative gives us +36. And we end up with 0. Again, we already know that that is a factor, so this has to be 0. So when we're breaking this down, we started with x to the 4th. If we're dividing that by an x to the 4th divided by x is going to give us x to the 3rd to start with. So there's our polynomial. And then we're going to take this polynomial and we're going to divide by the opposite sign of our factor, which would be x minus 4. And again, when we do synthetic division, it's back to the actual sign of the root that we got from Desmos. So 4 and x minus 4 are opposite. X equals 4 and x minus 4 are opposites. But then with synthetic division, we need the opposite number of our factor, our binomial factor anyways. And then we're not going back to the beginning. We're continuing to break this down. So the coefficients then that we're going to use are 1, -4, 9, and -36. So we're going to bring down our first term, which is 1. 1 times 4 is 4. Add these, we get 0. 0 times 4 is 0. It's going to give me a 9. 9 times 4 is 36. And when we add those, again, we end up with 0. Again, you need that, otherwise you did something incorrectly. So in this case, we started with x to the third. We're dividing by an x, which means we're going to have x squared plus 0x plus 9. So now we have a quadratic. We have multiple ways to solve a quadratic equation. It's really nice when we don't have an x term. So we just have x squared plus 9 equals 0. And since there's no x term, we can undo this backwards to find our last two roots. So subtract 9 from both sides, which means that x squared is going to equal negative 9. And then when we take the square root of either side, we need the plus or minus. Well, the square root of 9 is 3, but because it's negative, it's an imaginary unit. So our last two roots are plus or minus 3i. So one of these is 3i, and the other is negative 3i, and now we have all four roots of our polynomial equation. So in any order, it doesn't really matter, but we have negative 1, 4, 3i, and negative 3i. So again, I know this is one of the longer processes. It's one of the longest processes in Algebra 2. But the nice thing about virtual learning is that you can go back and you can rewatch and replay videos and retry things. You could start over with this whole equation and try it on your own and see if the answer that you got matches mine. But you have to do it and you have to practice it in order to understand what's going on with this process. So here's another one. Solve this by finding all roots. So our exponent is 4, our highest exponent, our degree of our polynomial, which means we're going to have 4 different solutions, or four different roots. Not necessarily different, because sometimes we can look at multiplicities as well, but we're going to have 4 roots, including multiplicities. So starting with Desmos, we have x to the 4th plus 4x to the 3rd minus x squared plus 16x minus 20. And then when we take a look at where our graph crosses the x-axis, we have negative 5 and positive 1. So again, 2 of our solutions right off the top of the bat. Negative 5 and positive 1. And then we have to use synthetic division with those, divide them out to figure out what our final 2 roots are going to be. So we're done with Desmos once we see where it crosses the x-axis. And again, we're taking our polynomial. We're going to be breaking it down by the opposite of negative 5, so that's going to be x plus 5. And then when we do synthetic division, it switches back to the same sign as what our root is. And our coefficients are 1, 4, negative 1, 16, and negative 20. So we're going to bring down our first term. We have 1 times negative 5 is negative 5. Add, we get negative 1. That's going to give us positive 5. This is 4. 4 times negative 5 is negative 20. Add those, we get negative 4. And then negative 4 times negative 5 is positive 20. Add those, we get 0. Again, you need 0. Don't get this confused with regular synthetic division. You can have different remainders when we're doing regular synthetic division. Just not when we're finding all of our real roots. So again, we started with x to the 4th. We're dividing by an x, which is going to give us a start of x to the 3rd. So plus 4x minus 4. And then we have to divide this polynomial, so that should be x to the 3rd, by x minus 1. And again, because our roots and our factors have opposite signs, with synthetic division we're back to 1, and then our coefficients are 1, negative 1, 4, and negative 4. So we're going to bring down our first term. 1 times 1 is 1. Add those, we get 0. 0 times 1 is 1. Add those, we get 5. Aha! 0 times 1 is 0. I knew something was a little off there. So 3 times 1 is 0. Add those, we get 4. And then 4 times 1 is 4. Add those, and we get 0. So in our next step, we started with x to the third. We're dividing it by an x. So that we're going to have x squared plus 0x plus 4. So again, this is nice because we have a 0x. You could still use the quadratic formula if you want to with this, but we just have x squared plus 4 equals 0. So we can undo this backwards, subtract 4 from both sides without our x term. We don't have to worry about completing the square or the quadratic formula. So x squared equals -4. Square root both sides, and that means that x is going to be plus or minus 2i. So our third root and fourth root in some order are positive 2i and negative 2i. Our degree of our polynomial is 4, and we have 4 roots. So we know we're done with our equation. Okay, so you have 4 of these then to practice. Some of them you can either solve by factoring or by using Desmos and then dividing from there. And then make sure that you get all of your roots. So with number 1, and again, make sure you show your work so I can see how you solve the equation. So this is degree 4. So you're going to have 4 solutions. And then the next one's degree 3. So we're only going to have 3 solutions. So 3 x values. This is degree 4. So you're going to have 4 solutions. So with this one, if you choose to use synthetic division, especially to find your rationals, make sure you have your placeholder zeros for 0x to the third and 0x when you go to do your synthetic division. With this one, you could also factor this. In order to figure out the zeros of your polynomial equation. And then with the last one, then again, you'll have 3. So this is a degree 3 polynomial. So you should have 3 solutions. And again, make sure that you show all your work. I know this is a long process. If you need help with it, you have to ask. And I can help you. I can set up a meeting with you. You can send me a message on my Google phone number. But you have to show work with this in order to get credit for doing this assignment. Okay, and then the last thing, this kind of goes back to what we did at first, so it's not really a brand new skill at all. The irrational root theorem. So if the square root of a is a root of a polynomial, then the opposite square root of a is also a root. So we actually looked at this, but we didn't really know what this theorem is. But in one of the last examples, we got x equals 1 plus the square root of 5. And our second root was 1 minus the square root of 5. And that comes into play because anytime you take a square root, you need the plus or minus in front. And then the complex conjugate root theorem. So if a plus bi is a root of a polynomial equation, then a minus bi is also a root. We will only look at this in terms of if we're given 3i, then negative 3i is also a root. So we'd have x plus 3i, and we would have x minus 3i. And that goes back to operations with complex numbers. Similarly, if we were given that 4i, negative 4i is a root, that means we would have x plus 4i and x minus 4i as factors. So anytime you see an imaginary, you need 2 factors. One's positive, one's negative. And anytime you see a root, you need 2 factors with 1 positive and 1 negative. So taking a look at that in action, here's example 3. So the simplest polynomial, or the simplest function with zeros, I, square root of 3, and 1. So again, anytime you see I, you're going to have x minus I and x plus I. And then anytime you see a square root, we would have x plus the square root of 3 And x minus the square root of 3. And then this is just like we did in example 1. If we have 1 as a root, then x minus 1 is going to be our factor. And this is going to give us our polynomial. So my biggest suggestion that I could give you for this, again, because multiplication is commutative, is multiply common or alike expressions together first. So the reason why we're going to do that is going to make it way simpler, and it's going to get rid of our square roots, and it's going to get rid of our imaginary units if we do that. So these two things are common or alike, x minus I and x plus I. So if we multiply those together, so technically it's x minus 1i and x plus 1i. So x times x is x squared. This is going to be minus 1ix. This is going to be plus 1ix. And then we would have minus 1, I times I is going to give us I squared. So remember, anytime you see I squared, that's equal to negative 1. So this is negative 1 times negative 1, which is just going to give us a positive 1. And if we have 1ix and negative 1ix, those are going to cancel out. So this is going to simplify to simply x squared plus 1. You can probably notice some patterns when you're doing this and multiply them together extremely quickly. And then the next one, so again, these are also like common or alike expressions. So if we multiply x plus the square root of 3 times x minus the square root of 3. It's going to give us x squared. It's going to give us x times the square root of 3. It's going to give us negative x times the square root of 3. And it's going to give us a negative square root of 9. So you multiply the outsides first. So negative 1 times negative 1 is negative 1. And then you multiply the insides when you multiply two radicals together. 3 times 3 is going to give us 9. So the square root of 9 is just going to give us plain old 3. So you can see that things are going to cancel out and simplify. It's going to make our problem a lot easier. These are going to cancel. Negative x times the square root of 3 plus x times the square root of 3. And then this is just going to simplify to x squared minus 3, because the square root of 9 is 3. So this is kind of long. We're going to have a 5th degree polynomial when we're finished with it. But that's the hard parts. And it's, again, really not that difficult if you kind of use some patterns. So if we FOIL these two next, then that's going to give us x squared times x squared is x to the 4th. Then we have 1x squared minus 3x squared, which would be minus 2x squared, and then minus 3. And then we still have to multiply that by x minus 1. And that's going to give us our polynomial. Again, if you prefer to use a box every time to multiply, then by all means go for it. But we're going to take x to the 4th times x, which is going to give us x to the 5th. And then x to the 4th times negative 1, which would be minus x to the 4th. And then negative 2x squared times x would be minus 2x to the 3rd. Negative 2x squared times negative 1 would be plus 2x squared, and then minus 3x, and then plus 3. And that's going to give us our polynomial p of x. This one is not as easy to check as number 1 because you can't really check the imaginary roots on a graph. And the radicals we're going to have to change over. But again, still worth double checking. So what we came up with is x to the 5th minus x to the 4th minus 2x to the 3rd plus 2x squared minus 3x plus 3. So there's one of my roots, there's another one, and there's a third one. So that's 1.732 and negative 1.732, which are approximations. So if I check out what the square root of 3 is, it's 1.732. So that's going to include both of these, the square root of 3 and the negative square root of 3. And then we can see 1, and then we just kind of have to guess and make sure that I is right, again, because you can't see it on a graph. And that's why the synthetic division is good, to find all of your roots for your polynomial equations. So essentially we're doing two inverse processes. One is taking the roots and finding the polynomial, and then one is taking the polynomial and finding the roots. So make sure that you do example 3 practice. Again, don't forget with I, you always have x plus 2i and x minus 2i anytime you have complex roots. And then the next one's just normal, so this would be x minus 2, and then same thing with 3, we would have x minus 3. So you're going to multiply those together and come up with your polynomial. And slow down, double check, make sure that you're doing it correctly. And then there's just 2 final questions then. Number 5 is more like example 1. There are no irrationals or imaginary or complex, but this one with the negative square root of 5, make sure that you do x plus the square root of 5 and x minus the square root of 5 when you are finding this. So this should be degree 3. So it's going to start with x to the third power, and this one should also be degree 3. And again, means it's going to start with x to the third power. This one is going to be degree 4, which means that your polynomials can start with x to the fourth power. So again, I know that this is not super easy. It's longer processes. It takes a little bit of time to work. So make sure that if you have questions, you're reaching out, you're asking if you need help. I would be happy to work with you. Just let me know a time that works for you and we can make it work.